Okay, welcome back. We're on to session 3 of the Soloclim Symposium. My name is Emma Greer. I'm a partner at Carlo Ratti Associati, where I direct our in-house think tank, CRATHink, and I'll be moderating today's session. For the next 90 minutes, we're going to be talking about climate responsive systems for outdoor climate adaptation. We've got a great lineup of speakers who I'd like to formally introduce. First, we have Matt Santamouris, Professor of High Performance Architecture at the University of New South Wales, connecting all the way from Australia. Professor Santamouris, do you hear us?
Yes, I'm here.
Good evening. Sorry to keep you up late. We also have my colleague, a Soloclim research fellow, Sinead Nicholson, who's been splitting her research term between the University of Kent and Carlo Ratti Associati. We've got Thomas Auer, the partner and managing director of climate engineering firm Transolar, and the professor of building technology and climate responsive design at TU Munich. Last but not least, we'll be joined by my other colleague, Marika Tomasi, who is also splitting her research term between Carlo Ratti Associati and the University of Kent. So this morning and earlier this afternoon, we heard about vegetation and water-based solutions. In this session, we're going to be talking about climate responsive design for outdoor spaces and talking about how to make cities really generally more livable and more resilient. In keeping with the other sessions, we're going to split the presentations into 2 groups. We're going to start with smaller or street scale solutions and then move on to city scale or urban scale solutions. And we've paired seasoned experts in the field with 25-minute keynotes with emerging young voices in the space of climate adaptation. So we're going to start with the smaller scale and move to the larger scale. Now, without further ado, let's turn to Professor Santamouris from the University of New South Wales. Professor Santamouris, the virtual floor is yours for the next 25 minutes.
Thank you very much. Thank you so much for the kind invitation. I hope that you can see my screen. Urban heat island is the more documented phenomenon of climatic change. It has to do with the higher temperatures in the center of cities or in the very dense parts of cities. Because of the positive thermal balance, in the urban environment compared to the surrounding, let's say, suburban or rural spaces. Do we have enough evidence and knowledge about, urban heat island? Of course, we have, actually data from more than, it's not moving. From more than 450 cities all around the world. And this is the more documented phenomenon of climatic change. I'm so sorry, there is a problem with my slides. Oh, yeah, okay. Do we have really data about, the urban heat island? Yes, we have data from about 450, let's say, cities all around the world where the urban heat island phenomenon is very well documented. And the amplitude of the phenomena may range from, let's say, 1 degree up to 10 degrees in some cities. In average, the urban heat island phenomena is something close to 4 or 5 degrees in different cities of the world. But urban overheating is not just, the increase of the temperature or just, the urban heat island. It has to do also with the increase of the duration of hot spells. If we try really to plot the duration of the hot spells in the Mediterranean area during, let's say, the last 100 years, you will see that the number of hours above 37 degrees, which are the green, let's say, bars, or above, let's say, above the red bars, or above, let's say, 40 degrees, the green bars, have increased tremendously during the very last years. In parallel, a part of the increase of the temperature in the cities and a part of the increase of the duration of the hot spells, we are facing a very important problem of magnitude and also frequency of, let's say, heat waves. If you try really to plot the heat waves and especially the frequency of the heat waves in Eastern Mediterranean, you will see that there's a tremendous increase during the last years. Of course, it is evident that urban heat island and urban overheating has a tremendous impact on our societies. And the impact, it has to do first with, let's say, the increase of the energy consumption, the increase of the peak electricity demand, problems on health, problems on survivability, problems on economy. I will try really to give you some recent data about what we know about the impact of urban heat island and urban overheating in our cities. And let's start with, let's say, the problem on energy. We know very well that actually urban heat island and urban overheating is increasing tremendously the energy consumption for, let's say, for cooling. And at the same time, it increases tremendously the peak electricity demand in our cities. But it's not just that. It increases also, let's say, the problems in, let's say, power plants, decreasing their efficiency and also increasing, let's say, the pollution which is generated by, let's say, the power plants during, let's say, the heat waves or the very hot period. Do we know exactly what is the impact of the urban heat island actually on the peak electricity demand and also on the energy consumption? Yes. This is very well documented with many recent studies that shows actually that the global energy penalty per, let's say, city surface is close to 2.3 kilowatt hours per square meter, or per degree of temperature increase is close to zero point 0.7, or if you like, per person is close to 230 kilowatt hours per person energy penalty because of, let's say, the heat island. And this brings us to the very important issue that has to do with the increase of the cooling demand during the next years. Because of the tremendous increase of the space that is occupied by families, the decrease of the family size, the increase of the temperature, the increase of the population, we're expecting a tremendous increase of the cooling demand by 2050. This is the actual demand, and this is the actual demand for cooling all around the world. There are three scenarios that really simulates the future energy demand for cooling. According, to a very conservative scenario, by 2050, we may increase, let's say, we may expect an increase of the cooling demand by 320%, or if you like, a very intensive development scenario, this increase may be as high as 200 and 270%. Just to understand that by 2050, just one Indian city, Mumbai, may present higher cooling energy demand than the whole United States. So given that, it is very important really to understand the impact of overheating and find solutions. But it's not just the increase of the energy demand because of the urban heat island. It creates important problems of air pollution, increasing the concentration of ozone because of the very important, let's say, pollution problems created by the photochemicals, reactions in the atmosphere. And most of the increase of the ozone in the atmosphere is because of the urban overheating. But it's not just that. We know, and this is very well documented, that for each degree of temperature increase in our cities, the pollution, let's say, released by the power plants, and especially the thermal power plants, is increasing by about 3.5%. So consider that in the day that you have a heat wave and the increase of the temperature may be as high as 10 degrees, the pollution released by the power plants may be as high as 35%. Unfortunately, the main problem that it is related to the urban overheating is not just the energy or the pollution. It has to do with low-income population. And we know very well that low-income population is living in, let's say, in the more deprived part of the cities and also in low-quality housing. So we have very well, let's say, documented during the very last years, recent years, that during, let's say, the extreme phenomena of heat waves, temperature indoors, may be as high as 40, 45 degrees. I show you recent measurements from a survey of about 150, let's say, low-income houses in Athens, Greece, that shows that at the end of the heat wave, we had almost 4 days continuously above 35 degrees, in indoor houses. This brings us to the very important problem of urban overheating, which is the problem of health. It is extremely well documented that because of the higher temperature, heat-related mortality is increasing almost exponentially above a threshold temperature. And this threshold temperature is not the same everywhere. For example, this is a graph for Athens that you see that above 32 degrees, heat-related mortality is increasing almost exponentially. And the same happens for most of the Mediterranean cities, where the threshold temperature may vary between 29 to 32 degrees. This is not the same for Northern European cities, for example, London or Stockholm or Helsinki, etc., where you can see that the threshold temperature is much lower, between 21 to 24 degrees. So we are not, let's say, we don't present the same sensitivity to heat. And this has to be taken into account once really we calculate the impact of urban overheating in our cities. And this is a very serious phenomenon. For example, in Sydney, actually, in the western part of the city where we have an important overheating, heat-related mortality during, let's say, the summer is 3 times higher than the heat-related mortality in the eastern part of the city because, of this overheating. And this really brings us to the importance of, let's say, the quality of the outdoor environment, and that counts very much. But recent studies that have been performed shows that in reality, the combination of the quality of, let's say, our housing together with the combination of the urban environment plays a tremendous role on, let's say, heat-related mortality, which is going to be the future major problem. These are the bad news. And let's go to the good news. Can we really face the problem of urban overheating? Yes. During the last 20 years, there's very intensive research on heat mitigation technologies, trying to develop methods, systems, techniques that really may decrease the temperature in our cities. You have already heard several presentations trying really to present which is the state of the art on evaporative technologies, on greenery technologies, and so on. I like really to concentrate on something that, in my opinion, is the most important, let's say, during the very last years, and that has received the more important, let's say, progress during the last 5-10 years. And this has to do with the development of materials, advanced materials for mitigation technologies. And I like to concentrate on 3 types of materials that are now developed and are commercially available. I will start with thermochromic materials for the building environment, and especially, for the urban environment and buildings, materials that may change their color as a function of temperature. So these materials may be, let's say, very absorbing during, let's say, the winter period, and so absorb heat and contribute to heating, but they may change their color and be reflected during the summer period. And you see some of these materials that have been developed during the very last years. These materials present a decrease of their surface temperature up to 20 degrees. So these materials may, let's say, contribute tremendously really to decrease the temperature in the urban environment. And if you don't believe me, you can see, let's say, the thermal graph in the right part of, let's say, the slide. During the very last years, we have a tremendous progress on thermochromic material using photonic materials, which really offer a tremendous stability. And these materials are almost now available into the market. The second family of, let's say, materials for mitigation technologies, which is a real revolution for the urban environment, has to do with the so-called photonic materials or daytime radiative coolers. Materials that present a very high reflectivity, but let's say may emit, or if you like, dissipate the excess heat to the space through the atmospheric window. So these are materials that really emit the excess heat to the space directly. These materials are developed, and for example, I show you some of the experiments we had last summer, December, in Australia, in the desert environment, and I like to show you the results. SuperCool materials, as we call them, present almost 20 degrees lower surface temperature than the ambient one under the sun. So imagine that the ambient temperature was 44 degrees, and the surface temperature of the materials was 25 degrees. These materials, which are now commercially available, are called SuperCool materials, are the best solutions really to decrease the temperature of our cities. You see, for example, the results of a recent study that we are carrying out in Riyadh, in Saudi Arabia. We're responsible for the whole mitigation project of the city of Riyadh. And you may see that by using SuperCool materials on the roof of buildings, we may decrease the peak ambient temperature in the city up to 4 degrees. This is of extreme importance, and it's the highest performance we may expect by using mitigation technologies. The main problem of these materials is that because of the very high dissipation they may present, we may have, let's say, an overcooling during, let's say, the winter period. But actually, there's the technologies that we have developed, and we can modulate both, let's say, the emissivity and the reflectivity. So these materials may be very reflecting and emissive during the summer, contributing to cooling, but at the same time, very absorbent where we are applying this kind of technologies. The last technology that I'd like to present you has to do with the so-called fluorescent materials, materials that are really quantum dots, means nanotechnologies, that do not absorb heat. Imagine that we have materials that do not absorb heat, or the heat which is absorbed is re-emitted immediately. This is something, let's say, very important for the heat and for the built environment. And actually, we have developed materials here in Sydney, fluorescent materials that may decrease the temperature of, let's say, of buildings by using these fluorescent materials up to, let's say, 20 to 25 degrees. So where we are actually, we started 15, 20 years ago using white materials, and we succeeded really to decrease the temperature of our cities by 0.5 degrees. Then we moved to infrared reflective, let's say, color materials. We could really decrease the temperature 0.6, 0.7 degrees. Actually, with the tremendous progress that we have using advanced materials in the built environment, we are able to decrease the peak temperature of cities up to 2.53 degrees. And there are more than 250 large projects all around the world. We are responsible for about 20 projects all around the world, big projects from Houston in the United States, Dubai, Riyadh, Calcutta, and Kuala Lumpur, and many projects in Australia. We expect with the new materials that we have developed to decrease the temperature of our cities up to 4 or 5 degrees. This is tremendous. This has a tremendous impact on energy consumption. Simulation of the energy consumption using, the SuperCool materials in the city of Riyadh, and simulation of about 4,000 buildings together with LBNL in Berkeley has shown that it is possible by using this kind of technologies to decrease the peak electricity demand for cooling up to 40%, which is a tremendous, really, potential. At the same time, for the city of Sydney, although we expect a tremendous increase of the temperature by 2050, by using mitigation technologies in the urban environment, combined with adaptation technologies, advanced buildings, we may decrease the cooling demand of our buildings up to 0 by 2050. The most important, however, is that the use of these materials decrease the temperature of our cities, and this contributes tremendously on, let's say, heat-related mortality. We know very well, actually, that by using, let's say, these materials and by decreasing the temperature by, let's say, or increasing the albedo of cities by 0.1, we may decrease the, let's say, heat-related mortality by 8%. And this is, let's say, something that is coming from, let's say, more than 50 studies all around the world. So I like to conclude. Actually, we have a very serious overheating problem. There are more than 450 cities, major cities all around the world that present such a big problem. And this has a tremendous impact on energy. It increases the energy consumption to 40–50%, depends on the city. It increases the peak electricity demand up to 10–15%, let's say, obliging utilities to build additional power plants. But the most important is that really it increases heat-related mortality by 30–40%. Do we have solutions? Yes, because of the very intensive research on mitigation technologies, including materials, greenery, evaporation, and many other things, we are able to decrease the peak temperature of cities now up to 2.5 degrees. There are more than 250 projects all around the world where really we have shown in large-scale, real-scale projects that we decrease the peak the peak temperature up to 2.5 degrees. We may decrease the energy demand up to 35%. We may decrease the peak electricity demand up to, let's say, 4–5%, and also decrease the heat-related mortality by, let's say, 20–25%. To do that, and I like to conclude with this, it is extremely important to understand that this is an interdisciplinary research. We need to collaborate with people working on all aspects, of urban climate. It's not just the work of the architect or the engineer or of the landscape engineer or of the economist or of the environmental, let's say, engineer. We have to work together, and we need really to combine our knowledge in order really to address in a holistic way and integrated way the real problem of overheating. Thank you very much.
Thank you very much, Professor Santamouris. You did a wonderful job of bridging two extreme scales from the city all the way down to the nano material or the quantum space. So before we head into a small Q&A session, I'd like to hand it over to Sinead, who's going to give us a 10-minute presentation on the research that she's been doing between the University of Kent and Carlo Ratti Associati. Please.
Thank you, and thank you, Professor Santamouris, for joining us from Australia. It's very nice to hear someone talking from home. I'm from Australia myself. Okay, so I'm researching the field of climate responsive solutions for outdoor climate adaptation on the street scale. And I'm working through the University of Kent and Carlo Ratti Associati, as Emma mentioned. And my supervisors are Professor Marilena Nicolopoulou and Professor Richard Watkins, as well as Monica Love and Juan Carlos Romero. So really at the heart of this issue of climate change is temperature. And biologically speaking, temperature affects everything. It influences all aspects of the physical environment and governs any process that involves a flow of energy, setting boundaries on what an organism can and cannot do. And that's the same for ourselves as humans. It affects where we can live and what we can do in those places. So that leads me to my question of how to design for outdoor thermal comfort at the street scale, and specifically how shade canopies, and as part of this project, I would like to design and prototype shade canopies as climate responsive systems, looking at how they can combine material, geometry, and the ability to interact with users to improve thermal comfort. And through this, answering this question and building this prototype, I would also like to contribute to a workflow that better integrates design and microclimate research. So this is a research by design methodology, which is kind of a looping process and a responsive system in itself. With my project, I start with a project proposal. I move on to this establishing a tool or a way of testing my design. And for me, in this case, I'm looking at environmental simulation at this first stage. And once I have that established, I can go between this simulation and prototyping, real-world prototyping, which can then be evaluated for its effect on users, microclimate, and also how designers can be implemented in this process. So this project covers three main areas: thermal comfort, which is the user's experience of microclimate; microclimate mitigation, which in urban design is covers strategies related to water, vegetation, shading, and materials; and responsive systems, which can help enhance how these microclimate mitigation affects thermal comfort by allowing them to adapt to ever-changing microclimate and user variables. So what is thermal comfort exactly? So this is the experience, the user's experience of microclimate. So it's affected by both the physical space, including the morphology, weather, and function of that space, as well as the individual's own ability to adapt. And that can be affected by their human characteristics, as well as the physical space and how it's designed. And it allows them to adapt behaviorally, physiologically, and psychologically. And why is this important? I mean, outdoor thermal comfort can be the difference between an outdoor space being used and not. And as COVID is emphasizing, we really need this outdoor space that makes cities livable. It's a place for refuge, it's a place for social gathering, it's a place for civic action. And these places are at risk due to global warming and the urban heat island effect. So we need solutions. And climate responsive shading canopy can offer a flexible design option that can be integrated both into existing places as well as into new design places. On the area of microclimate, it can interact, a shading canopy interacts with microclimate variables by affecting solar radiation. So it can block direct solar radiation hitting the user, and it can also regulate the radiant environment around them. So it affects how the heat is exchanged between the urban surfaces and the user. And it can respond to the microclimate potentially either through an extrinsic kind of active process. So actually CRA's own project, Sun and Shade, does this. The reflective discs are able to follow the path of the sun, reflecting solar radiation across the whole day. Or there's an intrinsic, a more kind of passive or embedded process. So this is an example of flectofilm, which is relying on the structure, the metal structure that bends as it heats up, which then opens the shading louver. So that's the microclimate. How can a shading canopy respond to users? Well, there are multiple design options to help a user to adapt or allow a user to adapt to thermal comfort, but a big one and an interesting one for designers is allowing choice, because when you can control your environment, you really start to feel, you give yourself more comfort about the space you're spending time in. And in a canopy, this could be on a very small scale level, interacting with the canopy itself. And sun and shade, actually, again, it allows the user to override the mechanical, the automated movement, so that they can choose their own level of solar radiation being reflected away or towards them. And it can also respond more to the city user needs on a larger scale, because it's an ephemeral, portable, adaptable kind of device. So you can, something like this shading canopy kit, a very simple design that was distributed to users in neighborhoods that were identified as being vulnerable to heat stress. So how to turn this theory into practice, because part of this project is also developing a design process. I've just been looking into this stage of having a tool to test the future prototype. And this means simulating outdoor thermal comfort, which is quite a complex topic. And there are some issues related to this, including a lack of data, especially for the actual microclimate, because often data is taken in the airport in semi-urban areas and not representing the physical place you want to design in, and time, because it's a very complex process and often simulation software can take 24 hours to simulate a 24-hour period. So I actually wanted to look at how to better integrate data collection. So on this side of things, I built my own little comfort station, which is actually directly corresponding to a parametric software, Ladybug Tools, that is used by architects already. And it also as a parametric software, allows you to change designs, change material properties, and select exactly what you want to simulate. So it really decreases the amount of time spent to do simulation. And so that is bringing me up to my next steps. Now that I have a tool established to help me design, I want to look at how a canopy and the material properties, the dimension, the angles can affect the user. And I also want to look at how that changes across various climates and seasons to create a shading canopy that's adaptable in many contexts. Thank you.
Thank you so much. I'm thrilled to see so many of CRA's projects in your presentation. I'm sure you're eligible for some sort of bonus for giving us so many plugs. So thanks a lot. We've got a few questions. Well, I've got a few questions. We've got a few questions from our online audience. If you have any questions for Professor Santamouris, do you want to kick it off?
I did have a question for Professor Santamouris, and I found your presentation really interesting and inspiring for my own project, actually. And I was just wondering, what is the kind of a density or coverage you need with these kind of materials to provide a cooling effect that really affects that gives the cities a benefit of climate adaptation?
Yeah, thank you very much for your question. Density is an important parameter. Is not the only parameter that affects, the whole, performance of the SuperCool or the cool materials. First, we have to understand, the reasons behind the overheating. For example, in Sydney or also in Riyadh or in Dubai, overheating is because of western winds coming from the desert. In this case, you have advection. And in this case, because of the advection, the higher the density, the lower the performance. Once the overheating is because of anthropogenic heat or because of the absorption of heat by materials without an important advection, density plays an important role, and the higher the density, the higher the performance. Once you are in a coastal area and you have a sea breeze, the use of cool materials or supercool materials may decrease the planetary boundary layer, so decrease, the strength of the, let's say, the sea breeze and decrease the amplitude or the magnitude of, let's say, of cooling. So depends. It depends on, let's say, the reasons behind, let's say, the overheating. And what really I like to tell you is that every city is a different case. Every city is a different case study. You cannot generalize and say, that cool materials perform very well here and not perform somewhere there. Or the same happens with green. For example, in Riyadh, the use of greenery without irrigation, it increases the temperature of the city by 1.5 degrees. It is very important to understand that mitigation has not really general, let's say, recipes to be used. It is very case specific, needs to know very good and very well, the building physics and the urban physics, and understand the reasons behind the overheating and find the proper, solutions for every case. General and empirical solutions, greenery is good, materials is good, water is good, is, something coming from, let's say, the last century.
Yeah, okay, very, very important point for me to keep in mind. Thank you.
We've got another question for you, Professor Santamouris, from our online audience regarding spectral selection. Mohammed asks, have you considered spectral selection of the solar spectrum? As you know, solar spectrum consists of different wavelengths with different thermal effects. Have you considered letting low energy wavelengths, the visible spectrum, in while blocking the high energy wavelengths? My understanding is that that's how radiative cooling materials work, but I am absolutely not the expert in the room, so I leave it to Professor Santamouris.
I'm not sure I have understood the question. So the question is, how really is related the short wave radiation against the long wave radiation? What is the question?
For mitigation techniques, have you considered spectral selection, letting in the low energy wavelengths, the visible spectrum, and blocking the high energy wavelengths?
To study and develop supercool materials, the whole spectrum, is analyzed in details. Very detailed, let's say, design tools, including, spectral tools and physical tools that take into account, every small detail of the solar spectrum are taken into account. Supercool materials are based on the very high reflectance of the materials in the short wave radiation, I mean, in the visible and the near infrared, and the very high emissivity in the, let's say, atmospheric window, not in the infrared, in the atmospheric window. Actually, cool materials that you can find everywhere now may present a high reflectivity in the visual part or in the infrared part, near infrared part, and a high emissivity in the, let's say, infrared spectrum. High emissivity in the infrared spectrum means that the materials emit a lot of radiation, but because the atmosphere is opaque, in this wavelength, this radiation is coming back and is reabsorbed by the materials. So in this case, the high emissivity, it doesn't really create any cooling effect. To have, important cooling effects, we should really dissipate the excess heat in the atmospheric window. In the atmospheric window, we don't have really a reflection from the atmosphere back to the material. So the material speaks directly to the space, which is at a temperature of 2K, very cool, and we dissipate the excess heat through the atmospheric window. Of course, the whole spectrum, it is taken into account, and every small detail about, the spectrum consideration and the spectrum performance of the materials, is taken into account.
Wonderful.
I have replied.
We're receiving a lot of questions. So if we don't get to all of the questions for this session, please tune in for tomorrow's roundtable discussion, and I'll try to work those in. We've got one question for Sinead from Ira Valdez. The question reads, for areas with high aspect ratios, such as narrow streets bounded by buildings with significant heights, do you think a canopy is still the right tool? It still has a significant impact, considering that the structures already cast a shadow at the street level?
Well, no. I mean, I think like coupled with a shading canopy has to be an analysis of the area and a strategic location of where you place these canopies. Like they're not, you can't just place them wherever you feel like it. Like there has to be a larger scale analysis, which is actually what's really nice about this Soloclim project is we're trying to link this small scale of my own prototype with the large scale urban analysis as well.
So as there's no city that can have the same strategy, there's no street that can have the same strategy, and an analysis is required for both. I have a question for the both of you to close this session, to Sinead and to Professor Santamouris. For young people or even more seasoned professionals who are looking to upskill and insert themselves in the design for climate adaptation space, where are there holes in the research? Where do we need to get up to speed? Where can people direct their studies? You mentioned in your own presentation, Professor Santamouris, that it's really a multidisciplinary effort. Where do we need to look to in the future to fill in the gaps and prepare for increasingly warmer climate events?
I'd like
to my colleague.
no, I would like to offer the first response to you, Professor.
Please go ahead, Professor Santamouris.
Okay, thank you so much. This is a very important question. I think that that during the last 10 years there's a tremendous progress on mitigation technologies, and as I mentioned before, this is a multidisciplinary, let's say, scientific topic, and has to be considered as a multidisciplinary. But what is more important during the last 10 years is that the whole scientific world moved from the empirism to the science, to the scientific, development. It is absolutely necessary to stop living with myths and move to the scientific knowledge, which is not the case, unfortunately. Many of the mitigation, studies, they are based on myths. So first task is to understand the science of mitigation. We are new on it, but we understand. Second, we have really to understand the reasons of the overheating. The reasons of the overheating are not the same everywhere. So it is very important to use very advanced techniques, for example, satellites, drones, mobile stations, whatever, in order really to understand the reasons of the overheating. If we don't know the reasons of the overheating, we risk to solve the wrong problem. Once this is done, once we know the reasons of the overheating, we should have a very good knowledge of the potential of the different mitigation technologies and also of the potential of their combination. For example, when cool materials or supercool materials are combined with greenery, they increase their performance by 30% because really they use the pressure difference that is created by the combination of them. It is very important to use very sophisticated and really good quality mitigation tools that calculate the real performance. This is not the case, actually. We have tools, but most of the tools, they don't use proper algorithms. For example, once we try to calculate the performance of greenery in the city, and it is well known that green infrastructure above a threshold temperature stops really to provide evapotranspiration because they keep their sap really to be protected. Actual, let's say, tools, they give you that there is a tremendous cooling, let's say, decrease, even if the temperature is very high, which is not the case. I will address it tomorrow. Recent research has shown that trees contribute to cooling, fantastic technology, up to a certain temperature. Above the threshold improves real or increased heating. This is the reason that during summer, in or heat waves inside parks, temperature may be higher than outside the parks. So what I like to tell you is that knowledge, real knowledge and not myths are very important. It's extremely important really to understand. Once we have this knowledge and we have the proper tools, then we can design. We have to learn through the implementation and the understanding of the others. We don't have to imitate. Someone has done this in Sydney, let's do the same in Dubai or in Netherlands or whatever. This is a big mistake. So in conclusion, we need to advance science. Stop to be empirism, stop the empirical approach, be scientific, understand the physics behind it, and then I think that we have a tremendous progress in the near future. Thank you.
Thank you. And
You'll have to keep it short.
yes, if I may say, like, exactly. I mean, we need science behind design, and that is what I'm working on right now really helps me understand this, because I'm looking at simulation and how the data and the simulation leads to a design, rather than just coming up with the idea itself and applying it. I want to start with understanding the environment using this, the data and the simulation, to apply it to design. And I think that's really important for designers. And, this honeybee tools, ladybug tools, really allows visualization and communication that's easy for designers to understand the effects.
Well, that's confirmation that Carlo Ratti Associati is going in the right direction if we've got yourself and Marika working alongside our design team to science-backed solutions for the different cities and spaces in which we work.